In this section, we'll introduce the ratio and the root tests. Beginning with the ratio test, and this is actually a really effective test that's pretty widely used. There are some conditions that have to meet before it can be used, but when it can, it's actually quite straightforward and a very clean result in the end. Now, the conditions that need to be met is that the numerator and denominator need to be going to infinity at much faster rates than one or the other before you can get a result. And I'll show you why that is in just a moment. But first, let's define the ratio test and then go from there. Okay, so the ratio test says let the sum from n equals 1 to infinity of a sub n be a series with non-zero terms. The problem with terms that are equal to 0 is we're going to be dividing, and when you have division and 0, things are likely to go poorly. So we define a value, rho, and it doesn't really matter if we give it a name or not. Effectively, we're just evaluating this limit as n goes to infinity of a sub n plus 1, so that's the n plus 1th term, divided by a sub n, and that's the nth term in the sequence. So when we divide those two, we get a ratio between how quickly a sequence is increasing in value or decreasing in value. And that measure we can actually use to determine if this thing is converging or diverging. Now, a lot of times when I work through this limit, I start the limit by working it out as, say, a sub n plus 1 times 1 over a sub n, and then just go ahead and invert the second fraction, because that's usually the first step in the process anyway. I'll show you through examples what I mean there, but regardless, once you calculate this limit, you're going to get a value. So that value could either be finite, or it could be infinite, or it could be 0. It's going to be positive because we're taking the absolute value of the terms in the sequence, so that would always result in a positive answer. And what we say here is that if the limit is between 0 and 1, then the series converges, and it's actually absolute convergence here. So we've ruled out the possibility of conditional convergence. So it's a bit stronger of a result for that reason. If rho is greater than 1 or infinite, then the series diverges. Then if rho is equal to 1, so if the limit value is equal to 1, the test does not provide any information. So we can just say basically the test fails, and then we have to go back and try a different method in order to get a result. But hopefully the advice that I give you today will give you a means of determining when it's appropriate to use the ratio test and when it's not, so that you won't run into that situation. But first, what I want to do is give you kind of an intuition as to how this is working. It's fairly understandable, but let's take a look at some graphs. All right, so let's take a look at a series that we know if it converges or not. So I'm going to pick on some P series because those are pretty easy to know what's happening. And let's just start with a harmonic series. That's pretty straightforward. So 1 over n, we know it diverges. So these are the terms in the sequence. And the ratio test effectively takes, like we would start with the second term. The y value there is 0.5. The y value of the first one is 1. So we take the ratio of those two terms. And if you'll notice, this is decreasing in value. So if we take those and divide, so 0.5 divided by 1, it gives us a number that is less than 1. All right, same thing if we go from 0.5 to the next value, so 0.33 divided by 0.5. If it's decreasing in value, we should get a number that's less than 1. Okay, that's why in the ratio test the value 1 is so important, because if it's bigger than 1, these ratios are bigger than 1, then it's diverging. If these ratios are less than 1, then it's converging, and then of course if it's equal to 1, we get no information. So that's exactly what we're doing here. We're just taking subsequent terms and dividing. So if it is decreasing, then these terms should be getting fairly close to one another as they flatten out. So as these terms flatten out and get close to each other, so like for instance, I've got 0.0556 divided by the previous one, which is 0.0588. The subsequent term is less, but it's only slightly less. So that ratio is getting close to 1. All right, so let's look at this in general. I'm just going to turn on the terms of the ratio test. So the terms of the ratio test here, as we can see, the first one's 0.5, just like we determined, then 0.67. And then as we continue to do this, we can see that the values of the ratios are clearly going to 1. So what that means is for the harmonic series, the ratio test fails. It can't tell us if this thing is converging or diverging. What we need is the difference in these ratios from one term to the next to be much different from one another. Right now, they're very close in value to one another. And so it's not changing enough for the ratio test to tell us that this is clearly converging or clearly diverging. Let's look at another one. So this one will be similar, but it's a p series again, 1 over n squared, but this time it converges. So let's take a look at the new terms. So the sequence terms are going to 0, and they're going to 0 faster than 1 over n. In fact, this one goes to 0 fast enough to converge. But if you'll notice, the ratio test still doesn't apply here. It's got the ratio of those terms still going to 1. So the test fails here. In fact, the ratio test is not great for polynomial functions, like if you have a polynomial over a polynomial. So I guess I should say a rational. In those cases, you'd probably want to use the limit comparison test. For the ratio test to be effective, you need something in the numerator that is changing much faster than what's happening in the denominator, or the reverse. So let's look at a different kind of series. Let's look at, say, 2 to the n over n squared. So 2 to the n is exponential, n squared is polynomial. So an exponential is going to grow much faster than a polynomial. Let's see what happens here. This should diverge. All right, so we can see the terms of the sequence here. They are clearly diverging. All right, if I zoomed back out a bit, you can see that these things are running off to infinity very quickly. Importantly, just grab the calculator here to show you, the ratio from subsequent terms. So from this term here in the sequence to this one, so 6.32 to 4. If I take 6.32 divided by 4, that gives me a ratio of 1.58. So when these are increasing in value, the ratio goes above 1. That's where we start getting a result here, because if the terms are increasing in value, they're running off to positive infinity, which means the ratios between subsequent terms would be bigger than 1, which is why then we can determine, because this one looks like the limit's probably 2, that's okay. The limit is not equal to 1. If it's 2, if it's bigger than 1, it diverges. So we're seeing that. In any series that did this sort of thing, that should be the case, as long as the numerator and denominator are changing fast enough with respect to each other. All right, let's reverse this, and let's look at n squared over 2 to the n. So now the denominator is growing faster than the numerator. All right, when I update that, now look at this pattern. So the terms of the sequence are going to 0. In fact, they're going to 0 very rapidly, okay? And they're going to 0 rapidly enough to where the ratios are starting to change and not limiting to 1. In fact, if we zoomed out far enough, we'd probably see that these are going maybe, looks like they might be going to a half, okay? But you can see that at the start, it's increasing, so these ratios are bigger than 1, but then it starts to decrease, and so we get less than 1, but they're decreasing fast enough. So like if I go from 0.78 to the next one, which is 0.56, so 0.56 over 0.78, that's decreasing fast enough to have a ratio that's less than 1. And the next one, is decreasing even faster and even faster. So they're going to 0 fast enough to get a result. Because this limit is between 0 and 1, we can say that this converges by the ratio test. So that's the idea. Let's take a look at actually working through some examples using the limit and seeing what results we can get. All right, in our first example, we want to use the ratio test to determine if this particular series converges or diverges. So in order to use the ratio test, what we will need to do is evaluate this limit as n goes to infinity of the ratio of the n plus 1th term divided by the nth term. All right, and as I said, what I'll generally do is calculate the n plus 1th term, and you just replace n with n plus 1, but then multiply by the inverse of the original series. So n factorial over 2 to the n. Now, the ratio test works especially well if you have terms that are involving factorials or exponentials, because the algebra that's involved there, 2 to the n plus 1, so that could be rewritten as 2 to the n times 2 to the first power. And n plus 1, you can always take the top item off of a factorial and make it a multiplier. So this could be n plus 1 times n factorial. And then we have an n factorial here and a 2 to the n there. And so the algebra with factorials and exponentials is such that we can get a lot of nice cancellation. And we get rid of those functions that we don't particularly know how to work with and algebraically with limits, leaving us with terms that we do know how to work with. So for instance, I'm now just doing the limit of 2 over n plus 1. So this is a rational function where the denominator is changing but the numerator is not. So we know that that limit is going to be 0. And the limit being 0, that's great. That is a result. And so we can say that this series converges by the ratio test. All right, let's try another one. So here I have the sum from n equals 1 to infinity of 2 to the n plus 1 over n squared. If I try to evaluate this limit required by the ratio test, I'll be doing the limit as n goes to infinity. The n plus 1th term, so this would be 2 times n plus 1 plus 1 over n plus 1 quantity squared times n squared over 2n plus 1. All right, so a little bit of algebra here. I could write the fraction on the left as 2n plus 3 over n squared plus 2n plus 1 times n squared over 2n plus 1. And these two fractions are multiplying. I could multiply these polynomials out. It turns out it's not really all that necessary. If you know enough about polynomials, effectively it's the degrees of the polynomials that matter. So like in the numerator, that's easy. That would just be 2n to the third plus 3n squared. The denominator is going to take a little time because I have to multiply a trinomial times a binomial. Ultimately, the two leading terms would multiply and give me the degree, so that would be the leading term, 2n squared, 2n cubed, plus there's going to be some other terms. They actually don't make a whole lot of difference in terms of going to infinity. What matters here is that the leading terms match in degree, and therefore the limit is equal to the ratio of the leading term coefficients, which is just 1. So that tells me that the test fails in this case. But if you'll notice, I have a polynomial over a polynomial, and the ratio test is not great for that type of situation. You need a numerator or denominator that's growing much faster than the other. And so two polynomials compared generally aren't changing fast enough to get a result with a ratio test. To get a result here, you would need to probably use the limit comparison test. I generally always use a limit comparison test for rational functions. It's a very clean result and generally very straightforward to do. All right, so to determine when, or to keep from running into this situation, it's a good idea to try and find out when this could happen so that you prevent yourself from running into the possibility. And here's a good sketch of what I do to try and avoid it. So the functions 2n plus 1 and n squared are both types of polynomial functions. And we see those, or the ratio test at least, sees those as going to infinity at about the same rate as each other. And it doesn't really matter the degrees, the ratio test just kind of sees them both going to infinity at about the same rate. So in order for the ratio test to work, you have to have functions that are growing very differently. So I rate the different functions by class, and I list them in terms, I call it velocity, but it's basically how quickly it's going to infinity. So we have the factorial function, so like n factorial, that's going to be going to infinity the fastest of all the types of functions we've seen so far. And that's going to infinity faster than any exponential function. It doesn't matter what the base is, but something to the nth power is not going to infinity as fast as the factorial. The polynomial goes even slower. So this is something like, n squared or something like that. It goes to infinity, but it's not nearly as fast as an exponential. And then finally we have our logarithmic, so like maybe the natural log of n. So going this direction, we get functions that are going to infinity slower. And going this direction, we get functions that are going to infinity faster. So using this list, you can actually get a pretty good idea of just looking at the function that you are working with and have a good indication if it's going to converge or diverge right off the bat. That doesn't help you prove that it converges or diverges. You do need to still do one of the tests that we've explored in class. But using this list, you can actually have a great idea as to what's going to happen. So if you get a result that's different, well, then you know that something may have gone wrong. So the ratio test then, as long as you have two different functions in separate classes, it's a great choice to use, especially if you have factorial and exponential pieces. So for instance, if I have the series n equals 1 to infinity of n squared over n factorial. So a polynomial is going to go to zero a lot slower, go to infinity a lot slower than a factorial function. So the denominator is growing a lot faster, which means this absolutely should converge. There shouldn't be any question about it. But that doesn't prove it. We need to do some sort of test to prove it. But it's nice to know that we've got a pretty good intuition that it's going to converge. Since these are in different function classes, the ratio test is probably a good idea. Let's give it a shot. So it's the n plus 1th term. Oops, n plus 1 in there. Times 1 over the nth term. Okay, so let's see what algebra we can do here. Generally, we need to start off by just kind of expanding some things out. So let me go ahead and write this as n squared plus 2n plus 1. In the denominator, I will take the n plus 1 off of the top of the factorial, because the nice thing there is that would cancel out the factorial completely from this limit. Now everything remaining is polynomial, and that should be a pretty easy way of determining a result here. So I would have n squared plus 2n plus 1 all over, in the denominator, n cubed plus n squared. The value of this limit, because the denominator is larger in the degree than the numerator, is going to be 0, and when that ratio is 0, that tells me that this converges. So we converge by the ratio test. All right, here's another example. And in this example, we have the function n to the n over n factorial. So it's not entirely clear which class of function this n to the n would be in, because usually if you have a constant as an exponent, that's a polynomial. But if your exponent is variable, then that means you have an exponential. So here, both the base and the exponent are variables. So it's not really either one. It's not really exponential or polynomial. We're not really sure what it is. So let's just see if we can figure out what happens with it. So ratio test might work here, because this should still have some of the properties of exponential functions. So algebraically, this should work out okay. N to the nth power, the nth term would be n plus 1 to the n plus 1th power. And then in the denominator, that would be n plus 1 factorial. Then multiply by the inverse of this, so n to the n factorial over n to the n. All right, so that can be, we can work with that a little bit. The numerator I could write as n plus 1 to the nth power times n plus 1. In the denominator, it would be, I could take n plus 1 off of the top of that factorial. And that's nice because n factorial definitely can cancel. And in fact, even this term, n plus 1, that can cancel as well. So this leaves me with a limit as n goes to infinity of n plus 1 to the nth power over n to the nth power. Or another way of expressing that, the limit as n goes to infinity, I could factor out the exponent and make this n plus 1 over n to the nth power, or rewriting that fraction, 1 plus 1 over n to the nth power. And this is a fairly common limit that we run into in calculus, and you might know the result of this, and if you do, that's fine, you can use that. If you don't, you probably would need to use a table here. I'm not sure L'Hopital's rule applies, so let's bring up the calculator and just use a table and figure out the value of this limit. So my function here is 1 plus 1 over n, so I'm just going to use, well, let's get back to there. 1 over x, there we go, and then raised to the x power. Now I'm not going to graph this, I'm just going to use a table, so let me make sure my table settings are proper. That looks great. And we'll let n go to infinity, so we'll do 10, 100, 1,000, 10,000, and so forth. Now, let me make this larger for you. If we look at what's happening here, it's definitely converging. You can see, like, we started with 2 for the whole number to start with, and then the first decimal started at 5, but then it sort of like settled in on 7, and then the second digit sort of settled in on 1, the third digit's kind of settled in on 8. So what's happening here is, you might recognize this number. It's settling in on the value e. So this limit is actually the definition of the value e, or one of the ways of deriving the value e. But it doesn't really matter that that's the case, it just matters that this is bigger than 1. And that tells me that this series diverges. And it diverges because the numerator is actually growing a whole lot faster than the denominator. So a function like n to the n grows faster even than the factorial.